Hello there, and welcome to Sleep with Science. I'm so glad you found your way here tonight. Maybe you've had a long day, filled with the bright noise of the world. Or perhaps you're simply the kind of person who prefers to drift off while contemplating the vast mysteries that stretch beyond our small corner of existence, rather than counting imaginary sheep jumping over imaginary fences. Either way, you're exactly where you need to be. You have nothing to do now but rest. Let your shoulders drop, your breathing deepen, and your thoughts slow to a gentle current. Feel gravity softening around you, as if you're floating just above the surface of sleep itself. Because tonight, we're embarking on a quiet journey into one of the universe's most profound mysteries. We're exploring black holes, not the Hollywood versions, not the sensationalized portals or cosmic vacuum cleaners, but the real phenomena grounded in physics and observation that challenge everything we thought we knew about space, time, matter, and light itself. Black holes are regions where gravity becomes so overwhelming that nothing, not even light itself, can escape their pull once it crosses a certain threshold. They are born from the deaths of massive stars, from collisions in the early universe, and perhaps even from conditions we've yet to fully understand. They bend space-time around themselves like heavy stones sinking into a cosmic fabric. They power the brightest objects in the universe while remaining utterly invisible themselves. They are endings and beginnings, destroyers and creators, mysteries wrapped in mathematics and observed through the clever tricks of modern astronomy. Over the coming hours, as your eyes grow heavy and your mind begins to wander through the borderlands of consciousness and dream, we'll travel together through the story of black holes. We'll trace their origins in theory, long before anyone believed they could be real. We'll follow the patient work of astronomers who discovered them, hiding in distant galaxies and even at the heart of our own Milky Way. We'll explore what happens to space and time near their boundaries, what it might be like to fall toward one, and why these objects might eventually evaporate into nothing after unimaginable spans of time. Some of what you hear tonight may surprise you. The universe has a way of being stranger and more beautiful than our intuitions suggest. But there's no need to hold on to every detail or remember every name. This is a journey for drifting, for letting the vastness of the cosmos cradle you gently towards sleep. Let the words wash over you like waves, carrying you deeper into rest with each passing moment. And before we begin, if these calm, curious explorations into the universe help you unwind at the end of your day, if they give you a peaceful way to close out the noise and settle into stillness, consider liking this video and subscribing to the channel. Your support helps others find their way here too. One sleepy soul at a time, all of us drifting together through the quiet wonders of science. Now, let your breathing slow. Let your body sink deeper into wherever you're resting. And let's begin our journey into the heart of darkness, where light cannot escape, but where understanding just might find a way through. The nature of black holes, a gentle introduction. To understand what a black hole truly is, we must first set aside some common misconceptions. Black holes do not roam through space, consuming everything in their path, like cosmic vacuum cleaners. They do not reach out with tentacles of darkness to snatch distant stars. They follow the same laws of gravity as any other massive object. If you were to replace our Sun with a black hole of exactly the same mass, Earth would continue in its orbit unchanged, receiving no light or warmth certainly, but not pulled into the darkness by some special force. What makes black holes unique is not that they have gravity, but rather the extreme concentration of their mass. Imagine taking something with the mass of several suns and crushing it down into a space smaller than a city, or taking millions or even billions of solar masses and compressing them into a region no larger than our solar system. The resulting density creates gravitational effects unlike anything else in the cosmos. At the heart of every black hole, according to our current understanding, lies something called a singularity. This is a point of infinite density where all the black hole's mass is concentrated. It's a place where the known laws of physics break down, where our equations produce infinities and our understanding reaches its limit. Whether singularities truly exist as mathematical points of infinite density, or whether quantum mechanics might smooth them out into something else, remains one of the deepest questions in theoretical physics. But surrounding this mysterious core is something more concrete, more observationally meaningful. It's called the event horizon. This is the defining feature of a black hole, the boundary that separates the interior from the rest of the universe. The event horizon is not a physical surface like the surface of a planet or a star. There's nothing there to touch, no material barrier. Instead, it's a mathematical boundary, a point of no return defined by gravity's strength. The event horizon represents the distance from the center where the escape velocity equals the speed of light. Escape velocity is the minimum speed needed to break free from a gravitational pull. On Earth, that's about 11 kilometers per second. On the surface of the Sun, it's over 600 kilometers per second. But at a black hole's event horizon, escape velocity reaches approximately 300,000 kilometers per second, which is the speed of light itself. Since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever escape. This includes light itself, which is why black holes are black. Any light that ventures too close, any photon that crosses that invisible boundary, is doomed to fall toward the center, unable to turn back, unable to climb out of the gravitational well. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole containing 1 million solar masses, the kind found at the centers of galaxies, the radius extends to roughly 3 million kilometers, about 4 times the distance between the Earth and the Moon. The relationship is direct and linear. Double the mass, double the radius of the event horizon. This radius is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who derived the first exact solution to Einstein's field equations of general relativity in 1916, just months after Einstein published his theory. Schwarzschild made this calculation while serving in the German army during World War I, remarkably deriving these equations by hand while stationed on the Eastern Front. He sent his results to Einstein, who was amazed by the mathematical elegance of the solution. Sadly, Schwarzschild died just months later from an illness contracted during the war, never knowing how his solution would become foundational to our understanding of these cosmic objects. The Schwarzschild solution describes what we now call a non-rotating, electrically neutral black hole. But real black holes, formed from the collapse of rotating stars or through the merger of massive objects, typically possess angular momentum. They spin, often at tremendous speeds. These rotating black holes are described by a more complex solution to Einstein's equations, worked out by the New Zealand mathematician Roy Kerr in 1963, and they're called Kerr black holes. Rotating black holes have some fascinating additional features. They drag space-time around with them, creating a region called the ergosphere, just outside the event horizon, where nothing can remain stationary. Even if you tried to hover in place, space-time itself would be spinning around the black hole, carrying you with it like a current. It's possible, in principle, to extract energy from this rotation through various mechanisms, though the practical challenges are immense. Some black holes might also carry an electric charge, though this is thought to be rare in nature. Charged matter falling into a black hole would quickly neutralize any significant charge. Still, the mathematical solutions exist. The Reissner-Nordström solution for non-rotating charged black holes, and the Kerr-Newman solution for rotating charged black holes. These complete the zoo of black hole types predicted by general relativity. But for tonight, as you rest and let these ideas drift through your mind, the key thing to understand is this. A black hole is a region of space-time where gravity has become so strong that a boundary forms, a point of no return called the event horizon, beyond which nothing can escape. Inside that boundary, all paths lead inexorably inward. Outside, the black hole's gravity behaves like that of any other massive object, following the inverse square law, weakening with distance. Black holes are not alien to the cosmos. They are a natural consequence of gravity, of matter collapsing under its own weight, taken to the most extreme conclusion. They are predicted by the mathematics of general relativity, and as we've discovered over the past several decades, they exist throughout the universe in remarkable numbers. How black holes are born, the deaths of stars. Most black holes form through one of the most violent events in nature, the death of a massive star. Stars spend most of their lives in a delicate balance. Nuclear fusion in their cores generates tremendous energy that pushes outward, while gravity pulls everything inward. As long as fusion continues, producing enough outward pressure, the star remains stable. But fusion requires fuel, and fuel eventually runs out. A star like our Sun will shine for about 10 billion years before exhausting the hydrogen in its core. When that happens, it will begin fusing helium into heavier elements, swelling into a red giant that engulfs the inner planets. Eventually, it will shed its outer layers as a planetary nebula, leaving behind a dense, Earth-sized remnant called a white dwarf. This white dwarf will slowly cool over trillions of years, radiating away its residual heat into space. But our sun will never become a black hole. It simply doesn't have enough mass. To create a black hole, you need a star that's truly massive, at least 8 to 20 times the mass of the sun, though estimates for the minimum mass vary depending on the star's composition and other factors. These massive stars live fast and die young. They burn through their nuclear fuel far more quickly than smaller stars, sometimes in just millions of years rather than billions. When a massive star exhausts its hydrogen, it begins fusing helium. When helium runs out, it fuses carbon and oxygen, then neon, then magnesium, then silicon. Each stage produces heavier elements and lasts for a shorter time. The fusion of silicon into iron marks the end of the road. Iron is the most stable nucleus in terms of binding energy. Fusing iron into heavier elements doesn't release energy. It requires energy. Once a massive star develops an iron core, there's no more fuel to burn. The core, now composed of iron ash, can grow no hotter. And without the outward pressure from fusion, gravity wins. What happens next occurs in less time than it takes to read this sentence. The core collapses catastrophically. In a fraction of a second, matter is crushed to incredible densities. Protons and electrons are squeezed together, forming neutrons and releasing vast numbers of neutrinos. The core becomes so dense that even these neutrinos, which normally pass through matter as if it weren't there, are trapped for a brief moment. The collapse continues until the core reaches nuclear densities, the same density as an atomic nucleus, but extending across kilometers. At this point, the core becomes incompressible and the collapse halts. But the outer layers of the star are still falling inward at tremendous speeds. When they slam into the rigid core, they bounce. This bounce, combined with the immense flux of neutrinos pouring out from the core, reverses the infall. An explosive shockwave forms, racing outward through the star's outer layers. The star explodes as a supernova, briefly outshining entire galaxies, ejecting its outer atmosphere into space at speeds of thousands of kilometers per second. The explosion seeds the surrounding interstellar medium with heavy elements forged during the star's life and in the supernova itself. Oxygen, carbon, silicon, calcium, iron, gold, uranium. We are made of this material. Every atom in your body, except for hydrogen and some helium, was created in the cores of stars or in supernova explosions. We are, quite literally, stardust, the remnants of ancient stellar catastrophes. But what remains after the explosion? The answer depends on how much mass is left in the core after the supernova has flung away the outer layers. If the remaining core is between roughly 1.4 and 3 solar masses, it becomes a neutron star, an object about 20 kilometers across, composed almost entirely of neutrons packed together as densely as an atomic nucleus. A teaspoon of neutron star material would weigh about 1 billion tons. If the core exceeds approximately 3 solar masses, however, even the pressure of neutrons packed together cannot resist gravity's inward pull. There is no known force strong enough to prevent further collapse. the core continues shrinking. It passes through the size of a neutron star, continues inward, and crosses its own Schwarzschild radius. An event horizon forms. The matter continues collapsing toward a singularity, but that collapse is now hidden from the universe behind the event horizon. A stellar mass black hole is born. These stellar mass black holes typically range from about 3 to a few dozen times the mass of the Sun. They can exist alone, drifting through space, invisible unless something comes close enough to interact with them. Or they can exist in binary systems paired with a companion star. In these cases, the black hole can pull matter from its companion, forming a swirling disk of material that heats up to millions of degrees and emits powerful X-rays. This is often how we detect stellar mass black holes, by observing these bright X-ray sources. The first object confirmed to be a black hole, Cygnus X1, was discovered in precisely this way. Astronomers detected a source of X-rays in the constellation Cygnus, the Swan, in 1964. By 1971, they had determined that these X-rays came from a massive, invisible object orbiting a bright blue supergiant star. The invisible companion was too heavy to be a neutron star. It was pulling material from its companion, and that material was emitting X-rays as it spiraled inward. Cygnus X1 became the first stellar mass black hole identified in our galaxy, located about 6,000 light-years from Earth. Since then, astronomers have identified dozens of stellar mass black holes in binary systems in our galaxy, recognizable by their X-ray emission. But these are surely just a tiny fraction of the total population. Most stellar mass black holes likely formed from solitary, massive stars that exploded without leaving behind a binary companion. These lone black holes emit no light and are extraordinarily difficult to detect unless something happens to pass very close to them. Estimates suggest there may be tens of millions, perhaps even 100 million stellar mass black holes scattered throughout the Milky Way galaxy. They are the invisible remnants of massive stars that died over billions of years, silently drifting through the galaxy, each one a point of such extreme gravity that nothing, once it falls past the event horizon, can ever emerge. The scales of darkness, types of black holes. Black holes come in various sizes, and this range spans an almost incomprehensible scale. Astronomers generally classify black holes into several categories based on their mass, though these categories are somewhat approximate, and the boundaries are not rigid. First are the stellar mass black holes we've already discussed, those born from the collapse of massive stars. These range from roughly 3 solar masses, the minimum needed to overcome neutron degeneracy pressure, up to perhaps 100 solar masses or more. The upper limit is less certain and depends on how stars of different masses and compositions collapse. Observations of black hole mergers detected through gravitational waves have revealed stellar mass black holes at the higher end of this range, some exceeding 60 or 70 solar masses. The formation of such massive stellar mass black holes poses interesting questions. Stars lose mass throughout their lives through stellar winds, and very massive stars lose tremendous amounts of mass this way. How do you end up with such a heavy black hole if the star loses so much mass before it dies? One possibility is that these massive black holes formed in environments where stars had lower metallicity, fewer heavy elements, which reduces the strength of stellar winds. Stars in the early universe, or in regions with less contamination from previous generations of stars, might retain more mass and produce heavier black holes when they collapse. Next, moving up the mass scale, we encounter what are called intermediate mass black holes, or IMBHs. These are black holes with masses ranging from roughly 100 to several 100,000 times the mass of the Sun. For many years, intermediate mass black holes were purely theoretical. We had evidence for stellar mass black holes and for supermassive black holes, but nothing in between. This gap was puzzling. It suggested that black holes might form through two entirely different mechanisms, depending on their mass, with a forbidden range in the middle. But recently, evidence has begun to accumulate for intermediate mass black holes. They may exist in the centers of dense star clusters called globular clusters, ancient spherical collections of hundreds of thousands of old stars. The motions of stars near the centers of some globular clusters suggest the presence of something massive and invisible. In 2024, observations of Omega Centauri, the closest and largest globular cluster to Earth, provided strong evidence for an intermediate mass black hole at its heart, with a mass around 20,000 times that of the Sun. This discovery is significant, not just because it fills a gap in our understanding, but because it may reveal how supermassive black holes formed. Perhaps they grew by consuming these smaller intermediate mass black holes, or perhaps intermediate mass black holes are the seeds from which supermassive ones grew. And that brings us to the giants, supermassive black holes. These monsters have masses ranging from hundreds of thousands to tens of billions of solar masses. They reside in the centers of most large galaxies, including our own Milky Way. The supermassive black hole at the heart of the Milky Way is called Sagittarius A star, and it has a mass equivalent to about 4 million suns. 4 million suns compressed into a region smaller than the orbit of Mercury. The event horizon of Sagittarius A star has a diameter of about 24 million kilometers, roughly 17 times the diameter of the Sun. This seems enormous, and it is, but it's still incredibly small compared to the galaxy itself. The entire supermassive black hole occupies a minuscule fraction of a tiny fraction of the galactic center. Yet, despite being so small, this black hole exerts a profound influence. Stars orbited at tremendous speeds. One star, designated S2, completes an orbit around Sagittarius A star in just 16 years, reaching speeds of about 5,000 kilometers per second at its closest approach. Watching Season 2 and other stars whip around this invisible point provided some of the strongest evidence that something extraordinarily massive and compact lies at the Milky Way's center, work that earned the Nobel Prize in Physics in 2020. Some supermassive black holes are far larger than Sagittarius A star. The black hole at the center of the galaxy, Messier 87, designated M87 star, has a mass of about 6.5 billion solar masses. Its event horizon spans nearly 40 billion kilometers across. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, showing M87 as a dark circular region surrounded by a bright ring of glowing gas. But M87 star is not the largest known. The galaxy Holmberg 15A hosts a supermassive black hole with a mass estimated at 40 billion solar masses. Some of the most distant quasars, powered by black holes in the early universe, appear to contain black holes with masses of 10 billion solar masses or more. How such enormous black holes formed so quickly after the Big Bang remains one of the great mysteries of astrophysics. The formation of supermassive black holes is not fully understood. They could have formed from the mergers of many smaller black holes over billions of years. They might have formed from the direct collapse of enormous gas clouds in the early universe, skipping the stellar stage entirely. They could have started as primordial black holes created in the first fraction of a second after the Big Bang. Or perhaps they grew from seed black holes created by the first generation of stars, which might have been far more massive than any stars that exist today. Each of these possibilities has evidence and challenges. What is clear is that supermassive black holes were present surprisingly early in cosmic history. The James Webb Space Telescope has observed galaxies less than 1 billion years after the Big Bang that already contain supermassive black holes. This rapid growth challenges our models and suggests that some of these black holes must have formed very efficiently, or that they started with unusually massive seeds. Finally, we come to a purely theoretical category: primordial black holes. These hypothetical objects would have formed not from stellar collapse, but from density fluctuations in the extremely early universe, within the first second after the Big Bang. During that time, the universe was extraordinarily dense and hot, and regions that happened to be slightly denser than average might have collapsed under their own gravity, forming black holes of various masses. Primordial black holes could, in principle, have any mass. They might be as light as a fraction of a gram, though such tiny black holes would have evaporated long ago through a process called Hawking radiation, which we'll discuss later. Or they might have masses comparable to asteroids, planets, or even stars. If primordial black holes exist, they could account for some or all of the universe's dark matter, the mysterious substance that outweighs visible matter but doesn't interact with light. No primordial black holes have been confirmed, but astronomers are actively searching for them. They would be difficult to detect directly since they emit no light, but their gravitational effects might be observable. They could cause subtle brightenings of distant stars through gravitational lensing, a phenomenon called microlensing. They might also betray their presence through gravitational waves if they merge with other black holes or dense objects. The existence of primordial black holes would have profound implications. They would provide a window into the earliest moments of cosmic history, into the density fluctuations that seeded all structure in the universe. They might solve the mystery of dark matter without requiring new particles beyond the standard model of physics. And they might explain how supermassive black holes grew so quickly by providing massive seeds already present in the early universe. So we have a spectrum from stellar mass black holes born from dying stars, each just a few times the mass of the Sun, through intermediate mass black holes, perhaps forming in dense stellar environments, to supermassive black holes, the giants at the hearts of galaxies, and perhaps primordial black holes, relics from the universe's fiery beginning. All are bound by the same fundamental physics, all defined by event horizons and singularities, all regions where gravity warps space-time so severely that the normal rules no longer apply. The theoretical foundation, Einstein's vision. Before black holes were discovered, before anyone knew they existed, they were predicted. They emerged not from observations, but from mathematics, from a theory about the nature of gravity, space, and time. That theory is Albert Einstein's general relativity, published in 1915. Einstein's insight was to recognize that gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of space and time around them, and other objects move along the curves of this warped space-time. Imagine space-time as a stretched rubber sheet. Place a heavy ball on the sheet and it creates a depression. A smaller ball rolling nearby will curve toward the depression, not because the heavy ball is pulling it directly, but because the sheet itself is curved. This is an imperfect analogy, since it still relies on our intuitive notion of down and uses gravity itself to illustrate gravity, but it captures something essential about Einstein's vision. In general relativity, the presence of mass and energy tells space-time how to curve, and the curvature of space-time tells mass and energy how to move. The relationship between matter and space-time is encoded in Einstein's field equations, a set of 10 coupled nonlinear partial differential equations that are notoriously difficult to solve in all but the simplest cases. One of the simplest cases is the space-time around a perfectly spherical, non-rotating, electrically neutral mass. Carl Schwarzschild solved Einstein's equations for this case in 1916, just months after the theory was published. His solution described the curvature of space-time around a point mass, and it contained something unexpected and disturbing. At a certain radius, now called the Schwarzschild radius, something strange happened to the equations. There appeared to be a singularity, a point where certain mathematical quantities became infinite. For a spherical mass of a given total mass m, this radius is directly proportional to m. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's about 9 millimeters. At first, physicists thought this mathematical singularity was just an artifact of the coordinate system Schwarzschild had chosen, similar to how the North Pole appears singular when you use latitude and longitude coordinates. And indeed, the Schwarzschild radius is a coordinate singularity in that sense. You can choose different coordinates where nothing appears unusual at that location. But there was another singularity in Schwarzschild's solution, at the center where r equals 0. This one was real. a physical singularity where space-time curvature becomes infinite and the known laws of physics break down. The interpretation remained unclear for decades. What did it mean for a mass to be compressed within its Schwarzschild radius? Could such a configuration actually exist in nature, or was it merely a mathematical curiosity? Einstein himself was skeptical. In 1939, he published a paper arguing that gravitational collapse to such extreme densities could not occur in nature. But other physicists were less certain. In the 1930s, J. Robert Oppenheimer and his student Hartland Snyder worked out the dynamics of a collapsing star. They showed that if a star's core exceeded a certain mass, no known force could prevent its collapse. It would shrink past its Schwarzschild radius and continue collapsing toward a singularity. General relativity predicted that this should happen, and there seemed to be no physical mechanism to prevent it. Still, many physicists resisted the idea. The notion of an object from which not even light could escape seemed too bizarre, too contrary to intuition. The term black hole wouldn't be coined until 1967 by physicist John Wheeler, who popularized the name during a lecture. Before that, such objects were called collapsed stars, frozen stars, or Schwarzschild singularities. What changed minds was a combination of theoretical advances and observational discoveries. In the 1960s, Roger Penrose and Stephen Hawking developed singularity theorems, proving mathematically that under general conditions, the formation of singularities is inevitable in general relativity. If you start with sufficient mass in a small enough region, and if the equations of general relativity are correct, then a singularity must form, hidden behind an event horizon. These theorems demonstrated that black holes were not mere mathematical oddities dependent on perfect symmetry or special conditions. They were generic, robust predictions of the theory. If general relativity was right, black holes should exist. And at nearly the same time, astronomers were discovering objects that seemed to fit the description. In the 1960s, the discovery of quasars, enormously bright sources of energy at the centers of distant galaxies, demanded an explanation. How could such compact regions produce so much power? The most plausible answer was accretion onto a supermassive black hole. The gravitational energy released by matter spiraling into a black hole can convert mass into energy far more efficiently than nuclear fusion, up to 42% efficient for matter falling into a rotating black hole, compared to less than 1% for nuclear fusion. By the 1970s, the existence of black holes was becoming widely accepted among astrophysicists. The observations matched the theoretical predictions too closely to ignore. X-ray telescopes found binary star systems where an invisible massive object was pulling material from a companion star, and the properties of these systems match what would be expected if the invisible object were a black hole. The case for stellar mass black holes grew stronger. At the same time, observations of galaxies suggested that supermassive black holes occupied their centers. The motions of stars and gas near galactic nuclei implied the presence of immense, concentrated masses. The only objects that could fit were black holes. General relativity had predicted them decades before they were found. The mathematics had foreseen what observation would later confirm. This is one of the great triumphs of theoretical physics, the ability of mathematical reasoning to reveal features of reality that are invisible to the naked eye, that operate on scales and in regimes far beyond everyday experience. Black holes exist because space-time can be curved so severely that it closes off a region from the rest of the universe. They exist because general relativity's equations permit and even require such configurations when enough mass is concentrated in a small enough region. They are real physical objects, consequences of gravity taken to its logical extreme. And they force us to confront profound questions about the nature of space, time, information, and quantum mechanics. As you drift towards sleep, consider this. Black holes are places where the equations that describe our universe begin to break down, where we reach the edge of our understanding. Yet even at that edge, the mathematics guides us, offering glimpses into the deep structure of reality, observing the invisible, finding black holes. If black holes emit no light, how do we know they're there? This question lies at the heart of black hole astronomy. We cannot see black holes directly, but we can infer their presence through their effects on their surroundings. The first confirmed black hole, Cygnus X1, was detected through its X-ray emission. In 1964, a sounding rocket carrying X-ray detectors flew above Earth's atmosphere, which blocks most X-rays from space. The detectors found several sources of X-rays, and one of the brightest was in the constellation Cygnus. Follow-up observations showed that this X-ray source corresponded to a binary star system, a bright blue supergiant star in orbit with something invisible. By studying the orbital motion of the visible star, astronomers could determine the mass of its unseen companion. The invisible object was too massive to be a neutron star, the only other known compact object at the time. It had to be something else. The X-rays were coming from material pulled from the supergiant star by the invisible companion's gravity. As this material spiraled inward, it formed an accretion disk, a swirling disk of gas and dust that heated to millions of degrees through friction and compression, hot enough to emit X-rays. This is a common way to find stellar mass black holes. Look for X-ray binaries, where an invisible massive object is accreting material from a companion star. Dozens of such systems have been found in our galaxy. The X-ray emission varies over time as the rate of accretion changes and as material in the disk orbits and heats unevenly. By studying these variations and the orbital dynamics, astronomers can constrain the mass of the invisible object and determine whether it exceeds the maximum mass for a neutron star, confirming it as a black hole. But not all black holes are in binary systems. Many formed from solitary stars and now drift alone through interstellar space. These isolated black holes are extraordinarily difficult to detect. Occasionally, though, they might pass in front of a distant star, and their gravity can bend the star's light through a process called gravitational lensing. Gravitational lensing is a direct consequence of general relativity. Light follows the curvature of space-time, so when light from a distant star passes near a massive object, its path is bent. If a black hole passes almost exactly between us and a background star, the black hole's gravity focuses the starlight, causing the star to appear briefly brighter. The amount and duration of the brightening depend on the mass of the lensing object. This technique, called microlensing, has been used to detect isolated stellar mass black holes. The Hubble Space Telescope has observed such events, watching distant stars brighten and dim as unseen objects pass in front of them. By analyzing the details of the brightening, astronomers can estimate the mass of the intervening object. If it's several solar masses but invisible, it's likely a black hole. Supermassive black holes at the centers of galaxies reveal themselves in different ways. Their enormous masses affect the motions of stars and gas in the galactic center. By tracking the orbits of stars over many years, astronomers can map the gravitational field and determine the mass and location of the central object. This is how Sagittarius A star, the supermassive black hole at the Milky Way's center, was confirmed. Teams led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute tracked stars in the galactic center for decades, watching them whip around an invisible point. One star, S2, was observed completing multiple orbits. The precision of these measurements, made using large ground-based telescopes equipped with adaptive optics to correct for atmospheric distortion, was extraordinary. The data showed conclusively that something with a mass of about 4 million suns occupied a region no larger than a few light hours across. No known object, except a black hole, could have such a large mass in such a small volume. This work earned Ghez and Genzel the 2020 Nobel Prize in Physics, shared with Roger Penrose for his theoretical work on black holes. Active supermassive black holes, those that are actively accreting large amounts of matter, are easier to detect. The accretion process releases enormous amounts of energy, making the galactic nucleus shine brightly across the electromagnetic spectrum. These active galactic nuclei, or AGN, can outshine the entire galaxy in which they reside. The brightest AGN are called quasars, short for quasi-stellar radio sources, because when they were first discovered in the 1960s, they looked like stars, but emitted strong radio waves. It took years to realize that quasars are not stars at all, but the brilliantly glowing disks of material around supermassive black holes in distant galaxies. Some quasars are so bright that they can be seen from billions of light years away, shining like beacons from the early universe. Quasars and other AGN allow us to study black holes that are too distant for us to resolve individual stars orbiting around them. The light from the accretion disk, the jets of material launched from near the black hole's poles, and the gas clouds surrounding the nucleus all carry information about the central black hole's mass and properties. Techniques like reverberation mapping measure the time delay between brightness variations in the accretion disk and changes in the surrounding gas clouds, allowing astronomers to determine the size of the region and infer the black hole's mass. In 2015, the Laser Interferometer Gravitational Wave Observatory, LYGO, opened an entirely new window for detecting black holes. LIGO doesn't look for light at all. It listens for gravitational waves, ripples in space-time itself produced by accelerating masses. When two black holes orbit each other and eventually merge, they produce gravitational waves that travel across the universe at the speed of light. On September 14, 2015, LIGO detected the gravitational waves from two black holes with masses of roughly 29 and 36 solar masses, spiraling together and merging into a single black hole about 62 solar masses. The remaining 3 solar masses were converted into pure gravitational energy, radiated away in the final fraction of a second of the merger. For that brief moment, the merger released more power than all the stars in the observable universe combined. This detection was revolutionary. It confirmed the existence of gravitational waves a century after Einstein predicted them. It provided direct evidence that black holes merge, and it allowed astronomers to study the properties of black holes through the gravitational waves they emit. Since that first detection, LIGO and its partner Observatory Virgo in Italy have detected dozens of black hole mergers, along with neutron star mergers and other exotic events. Each detection adds to our understanding. By analyzing the gravitational wave signal, astronomers can determine the masses and spins of the merging black holes, how far away the event occurred, and even test whether the merger behaves as general relativity predicts. So far, general relativity has passed every test. The mergers behave exactly as the equations predict, even in these extreme conditions where gravity is strong enough to warp space-time dramatically. But perhaps the most stunning confirmation of black holes came in 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The EHT is not a single telescope, but a network of radio telescopes scattered across the globe, working together to create Earth-sized virtual telescope with unprecedented resolution. The EHT observed M87 star, the supermassive black hole at the heart of the galaxy Messier 87, about 55 million light-years from Earth. The resulting image showed a dark circular region, the black hole shadow, surrounded by a bright ring of glowing gas in the accretion disk. The image matched theoretical predictions from general relativity remarkably well. The shadow's size, shape, and brightness distribution all aligned with what was expected for a rotating black hole of 87's mass. In 2022, the EHT released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. This image was more challenging to produce because SGR A star is much smaller than M87 star, and the gas orbiting it changes on timescales of minutes. The team had to develop sophisticated algorithms to average many observations and reconstruct a coherent image. But the result was similarly striking: a bright ring around a dark shadow, visual confirmation that our galaxy harbors a supermassive black hole at its heart. These images are historic. They represent the first direct visual evidence of the event horizon, the boundary of a black hole. They show us, for the first time, what space-time looks like when it's curved so severely that light cannot escape. And they confirm, once again, that general relativity's predictions hold true even in the most extreme environments. So we find black holes through many methods. X-ray emissions from accretion, the motions of stars, gravitational lensing, gravitational waves, and now direct imaging of the shadow cast against glowing gas. Each technique adds another piece to the puzzle, revealing these invisible objects through the ways they bend, heat, pull, and warp everything around them. The extreme physics. Near a black hole. What would it be like to approach a black hole? This question has fascinated scientists and the public alike for decades. The answer reveals some of the most counterintuitive and extreme physics in the universe. Let's imagine a journey toward a stellar mass black hole, say one with 10 times the mass of the Sun. From far away, its gravitational influence is unremarkable. It pulls on you according to the inverse square law, just like any other massive object. If you're in orbit around the black hole, you simply follow your orbital path, experiencing weightlessness like an astronaut on the International Space Station. But as you get closer, things begin to change. The gravitational field grows stronger, and more importantly, the gradient in the gravitational field increases. Gravity pulls more strongly on parts of you that are closer to the black hole than on parts that are farther away. This difference creates what are called tidal forces. Tidal forces are not unique to black holes. The moon raises tides on Earth through the same mechanism. The moon pulls harder on the side of lunar Earth facing it than on the far side. The difference in gravitational pull stretches Earth slightly, raising tides in the oceans. But the tidal forces near a black hole are far, far stronger. Imagine falling feet first toward the black hole. Your feet are closer to the black hole than your head, so they're pulled more strongly. The difference grows as you descend. The tidal force stretches you, pulling your feet downward and your head upward. At the same time, you're compressed from the sides, as all gravitational field lines point toward the center of the black hole. This stretching and squeezing effect is called spaghettification, a term popularized by Stephen Hawking. It's a real physical phenomenon, though the name is informal. If you fell toward a stellar mass black hole, spaghettification would become significant well before you reach the event horizon. Long before crossing that boundary, the tidal forces would exceed your body's structural strength. You would be stretched into a long, thin stream of atoms, crushed horizontally and elongated vertically. The exact distance at which spaghettification becomes fatal depends on the black hole's mass. For a black hole with 10 solar masses, the tidal forces would tear a human body apart at a distance of roughly 700 kilometers from the event horizon, which for such a black hole has a radius of about 30 kilometers. You wouldn't survive to cross the boundary. But here's something remarkable. For a supermassive black hole, spaghettification is far less severe at the event horizon. The tidal forces depend not just on the strength of gravity, but on how quickly gravity changes with distance. For a more massive black hole, the event horizon is larger, and the gradient is gentler at the boundary. Consider a black hole with 1 billion solar masses, like those found in large quasars. Its event horizon has a radius of about 3 billion kilometers. At the event horizon itself, the tidal forces on a human body would be imperceptible. You could cross the event horizon without feeling anything unusual. You wouldn't be spaghettified until much later, deeper inside the black hole, closer to the singularity where tidal forces eventually become extreme. This is one of the paradoxes of black holes. Crossing the event horizon of a supermassive black hole would be gentle, almost uneventful. You might not even notice the moment you pass through. There's no barrier, no wall, no sudden change. The event horizon is just a place in space-time where, if you do the math, you realize you can't get back out. But locally, at that moment, nothing dramatic happens. Still, something profound occurs, something that challenges our intuitions about time and space. From your perspective, falling in, time continues normally. You don't feel time slowing down. But to an observer watching from far away, something very different happens. General relativity predicts that time passes at different rates in different gravitational fields. The stronger the gravitational field, the slower time passes relative to a distant observer. This effect, called gravitational time dilation, has been measured precisely using atomic clocks at different altitudes on Earth. Clocks at higher altitudes, where gravity is slightly weaker, tick fractionally faster than clocks at sea level. Near a black hole, this effect becomes extreme. As you approach the event horizon, time slows down more and more from the perspective of someone far away. If you were falling toward the black hole while sending radio signals back to a distant observer, those signals would become increasingly redshifted, their frequency dropping lower and lower. The time between your signals would grow longer and longer, as measured by the distant observer. To the distant observer, you would appear to slow down as you approach the event horizon. You would take longer and longer to travel each successive meter. Your image would grow dimmer and redder as the light from you is stretched to longer wavelengths. You would appear to freeze at the event horizon, never quite reaching it, fading from view as your light becomes too faint and redshifted to detect. But from your perspective, none of this happens. Your watch ticks normally. You fall through the event horizon in a finite amount of your own time. You don't slow down, and you don't notice crossing the boundary. The contradiction is resolved by recognizing that there's no universal notion of simultaneous events. What the distant observer sees as frozen at the event horizon is not the same as what you experience. You experience crossing the horizon and continuing inward, but the light signals carrying that information never escape to inform the distant observer. Once inside the event horizon, your fate is sealed. All paths lead inward. No matter what direction you try to move, no matter what you do, you will reach the singularity in a finite amount of your own time. The singularity is not a place you can avoid by clever maneuvering. It's in your future, as unavoidable as next Thursday. What happens at the singularity? We don't know. General relativity predicts that tidal forces become infinite, that space-time curvature diverges. But most physicists believe this signals the breakdown of general relativity rather than actual infinities in nature. A complete theory of quantum gravity, which would describe the behavior of space-time at the smallest scales, would likely replace the singularity with something else. though we don't yet know what. This is one of the great mysteries at the heart of black holes. What lies at the center? Does the singularity exist as a point of infinite density? Or does quantum mechanics smooth it out into a region of extreme but finite curvature? We have no way to observe it directly, since the event horizon prevents any information from escaping. The interior of a black hole is, in a very real sense, cut off from the rest of the universe. Whatever happens there is hidden behind a one-way membrane in space-time. Yet even with these limitations, general relativity makes startling predictions about the interior. One of the strangest is that inside the event horizon, space and time exchange roles. Outside, you can move freely in space, but you're dragged inexorably forward in time. Inside the event horizon, the singularity is not a place in space, but a moment in time, your future. You can no more avoid it than you can avoid tomorrow. The physics near black holes is extreme, counterintuitive, and thoroughly tested by observations. Time dilation, spaghettification, the event horizon as a point of no return. These are not speculative ideas, but consequences of general relativity that have been confirmed directly or indirectly through decades of observations. They reveal a universe far stranger than our everyday experience suggests, one where gravity can warp space-time so severely that the normal rules no longer apply. Black holes that feed, accretion disks, and quasars. Not all black holes are solitary and silent. Some actively feed, pulling in material from their surroundings. When they do, they become some of the brightest, most energetic objects in the universe. Consider a black hole in a binary system with a normal star. The black hole's gravity pulls matter from the companion star, especially if the star has swollen into a giant and overflows its Roche lobe, the region where its gravity dominates. Gas streams from the star towards the black hole. But this gas doesn't fall straight in. It has angular momentum, a tendency to orbit. As it spirals inward, conservation of angular momentum causes it to move faster and faster. The gas collides with other infalling material, forming a flattened rotating disk called an accretion disk. Friction and viscous forces within the disk cause it to heat up. Material spirals inward, losing angular momentum through these forces, gradually working its way toward the black hole. As the gas gets closer to the event horizon, it moves faster and the temperature rises. The inner regions of the disk can reach temperatures of millions of degrees. At these temperatures, the disk emits intense radiation, primarily in X-rays. This radiation is powered by gravitational potential energy. As material falls deeper into the black hole's gravitational well, it loses potential energy, which is converted to kinetic energy and then, through collisions and friction, to thermal energy and radiation. The efficiency of this process is remarkable. Nuclear fusion, which powers stars, converts about 0.7% of mass into energy. Accretion onto a black hole can convert up to about 42% of the infalling mass into radiated energy if the black hole is spinning rapidly. This makes accretion onto black holes one of the most efficient energy generation processes in the universe. For stellar mass black holes, this accretion produces X-ray binaries, which are detectable with X-ray telescopes. But for supermassive black holes at the centers of galaxies, the scale is far larger. When a supermassive black hole accretes matter, it can outshine the entire galaxy. Active galactic nuclei, or AGN, are powered by supermassive black holes feeding on gas and stars in the galactic core. The accretion disk around a supermassive black hole can be light years across, with material spiraling inward at high velocities. The disk emits radiation across the electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The spectrum and variability of AGN allow astronomers to study the accretion process in detail. The disk's brightness varies as clumps of material fall in, and as instabilities develop, the light from the disk causes nearby gas clouds to glow, and by measuring the time delay between variations in the disk's brightness and changes in the gas clouds, astronomers can map the structure around the black hole. Quasars are the brightest type of AGN. They are so luminous that they can be seen from billions of light years away from the very early universe. A typical quasar emits hundreds of times more energy than the entire Milky Way galaxy, and that energy comes from a region no larger than our solar system. How does such a small region produce so much power? The only plausible explanation is a supermassive black hole with millions or billions of solar masses accreting matter at a tremendous rate. To power a bright quasar, the black hole must consume roughly the mass of one sun every few years. Over millions of years, this adds up, and the black hole grows ever larger. Quasars were much more common in the early universe, when galaxies were still forming and merging and gas was more abundant. Today, most supermassive black holes, including the one at the center of the Milky Way, are relatively quiet. They're not accreting much material, so they don't shine brightly. Sagittarius. A star, for instance, is currently very dim. It's consuming only a trickle of gas, far less than one Earth mass per year. But this wasn't always the case. Evidence suggests that many galaxies, including the Milky Way, went through active phases in their past when their central black holes were far more luminous. Large bubbles of hot gas extending above and below the Milky Way's center, called the Fermi bubbles, may be remnants of a period of intense activity a few million years ago when Sagittarius, a star, was feeding more vigorously. Accretion disks around black holes also produce jets, narrow beams of material launched at nearly the speed of light from the regions near the poles of the black hole. These jets can extend for thousands or even millions of light years, far beyond the galaxy itself. They emit intense radio waves and, in some cases, high-energy gamma rays. The exact mechanism that launches these jets is not fully understood, but it involves magnetic fields threading through the accretion disk and the frame-dragging effects of a rotating black hole. The black hole's spin twists space-time around it, and magnetic field lines anchored in the disk can extract energy from the black hole's rotation and channel it into the jets. The jets from supermassive black holes can have profound effects on their host galaxies and beyond. They heat the surrounding gas, preventing it from cooling and forming new stars. This feedback mechanism is thought to regulate the growth of galaxies. Without it, galaxies might form stars too rapidly and exhaust their gas supplies. The jets also inject energy into the intergalactic medium, affecting the large-scale structure of the universe. Active galactic nuclei and quasars allow astronomers to study black holes in ways that would be impossible with quiescent black holes. The light from the accretion disk and jets provides a wealth of information. By observing how the light varies, the spectrum of emitted radiation, and the structure of the jets, astronomers can infer the mass, spin, and accretion rate of the central black hole. These observations also test general relativity in extreme conditions. The light from the accretion disk is emitted from very close to the event horizon, where space-time is severely warped. Features like the broad iron emission lines seen in AGN spectra are shaped by relativistic effects. Doppler shifting from the disk's rapid rotation, gravitational redshift, and the bending of light by the black hole's gravity. These effects can all be modeled using general relativity, and the observations matched the predictions remarkably well. So when black holes feed, they don't just grow, they illuminate the universe, producing some of its brightest objects and shaping the evolution of galaxies. The energy released by accretion can outshine entire galaxies, and the jets launched from near the event horizon can reshape the intergalactic medium on the largest scales. Feeding black holes are not just passive consumers of matter, but active participants in cosmic evolution. Ripples in space-time, gravitational waves, and black hole mergers. On September 14th, 2015, at 9:51 UTC, both of the Laser Interferometer gravitational wave observatory's detectors, one in Louisiana and one in Washington state, measured a faint signal. The signal lasted less than a second, a characteristic chirp rising in frequency and amplitude before cutting off abruptly. That chirp was the sound of two black holes, each roughly 30 times the mass of the Sun, spiraling together and merging 1.3 billion light-years away. It was the first direct detection of gravitational waves, ripples in space-time itself, confirming a century-old prediction of general relativity and opening an entirely new way to observe the universe. Gravitational waves are disturbances in the fabric of space-time, generated when massive objects accelerate. Any accelerating mass produces gravitational waves, even you waving your hand. But the waves from everyday objects are unimaginably faint. To produce detectable gravitational waves, you need extraordinarily massive objects undergoing violent acceleration, like two black holes orbiting each other at a significant fraction of the speed of light. As two black holes orbit, they lose energy by radiating gravitational waves. This causes them to spiral slowly inward, orbiting faster as they get closer. The process can take billions of years for widely separated black holes, but it accelerates dramatically in the final stages. In the last few seconds before merger, the black holes are orbiting each other hundreds of times per second, moving at substantial fractions of the speed of light. The final merger releases an enormous amount of energy in gravitational waves. In the event detected by LIGO on September 14th, 2015, About 3 solar masses worth of energy was converted into gravitational waves in the final fraction of a second. For that brief moment, the merger released more power than all the stars in the observable universe combined. The resulting gravitational wave stretched and squeezed space-time as it passed through Earth, changing the distance between points by less than 1/10,000th the diameter of a proton. Detecting such a tiny effect required one of the most sensitive instruments ever built. Each LIGO detector consists of 2 4-kilometer-long arms arranged in an L shape. Laser light bounces back and forth along these arms, and when a gravitational wave passes through, it stretches one arm while squeezing the other, changing the interference pattern of the laser light by a tiny, measurable amount. LIGO is so sensitive that it can detect vibrations from trucks driving miles away, ocean waves breaking on distant shores, even the quantum fluctuations of light itself. To isolate the gravitational wave signal, the detectors use sophisticated noise cancellation techniques and compare signals between the 2 sites. A gravitational wave passing through Earth should appear in both detectors, separated by the light travel time between them, providing a way to confirm that a detection is real. The September 2015 detection was extraordinary, not just because it was the first, but because the signal was so clear. The waveform matched theoretical predictions from general relativity with remarkable precision. By analyzing the signal, scientists could determine the masses of the 2 black holes, how far away they were, and even the orientation of their orbital plane. Since that first detection, LIGO, joined by the Virgo detector in Italy and later by Kagra in Japan, has detected dozens of black hole mergers. Each one adds to our understanding of how black holes form, how they merge, and how common they are in the universe. Some of these mergers have produced surprises. The black holes detected by LIGO are often more massive than expected from models of stellar evolution. Some weigh 50 or even 70 solar masses, larger than most models predict for black holes formed from single collapsing stars. This suggests that some black holes might form through different channels, perhaps from the mergers of smaller black holes, or from massive stars in low metallicity environments, where stellar winds are weaker. On August 17th, 2017, LIGO and Virgo detected gravitational waves from a different type of event, the merger of 2 neutron stars. Unlike black hole mergers, which produce only gravitational waves, the neutron star merger also produced a brilliant flash of light visible across the electromagnetic spectrum, from gamma rays to radio waves. This was the first multi-messenger observation of gravitational waves and light from the same event. The neutron star merger provided unprecedented insights. The gravitational wave signal allowed astronomers to measure the masses and spins of the neutron stars. The electromagnetic emission revealed details about the merger process, the formation of a jet, the synthesis of heavy elements like gold and platinum in the debris, and the properties of matter at nuclear densities. Combining gravitational wave and electromagnetic observations gives a much richer picture than either could provide alone. Gravitational wave astronomy is transforming our understanding of black holes. For the first time, we can study black holes not through their interaction with light or matter, but through their interaction with space-time itself. Gravitational waves carry information about the masses, spins, and orbital dynamics of merging black holes that cannot be obtained any other way. The detections also test general relativity in one of its most extreme regimes. Black hole mergers involve velocities approaching the speed of light, gravitational fields strong enough to warp space-time dramatically, and rapid changes in space-time curvature. General relativity predicts precisely what gravitational waves such mergers should produce, and so far, every detection has matched those predictions. The theory holds up even under these extreme conditions. Looking ahead, new gravitational wave detectors are being planned. The Laser Interferometer Space Antenna, LISA, will be a space-based detector consisting of 3 spacecraft separated by millions of kilometers. LISA will detect lower frequency gravitational waves than ground-based COSIS detectors, waves produced by the mergers of supermassive black holes at the centers of galaxies. When galaxies collide and merge, their central black holes eventually sink toward the center of the merged galaxy and merge themselves, producing gravitational waves that LISA will detect. LISA will also be sensitive to other sources, the inspirals of stellar mass black holes into supermassive black holes, a process called an extreme mass ratio inspiral, and potentially even gravitational waves from the early universe, relics of cosmic inflation or phase transitions shortly after the Big Bang. Gravitational wave astronomy has given us a new sense, a way to hear the universe rather than just see it. The chirps of merging black holes are, quite literally, sounds from the cosmos, vibrations in space-time that we can convert into audio and play through speakers. The universe sings, and now we can listen. Peering into the abyss, the Event Horizon Telescope. For decades, black holes were indirect inferences deduced from their effects on nearby matter, from the orbits of stars, from jets and accretion disks. But in April 2019, something changed. The Event Horizon Telescope collaboration released an image that made headlines around the world, the first direct visual evidence of a black hole. The image showed a bright ring of glowing gas surrounding a dark central region. That dark region was the shadow of the supermassive black hole at the center of the galaxy, Messier 87, designated M87 star. The shadow itself is about 2.5 times larger than the event horizon, created by light that passes close enough to the black hole to be bent around it, but not captured. The EHT is not a single telescope, but a global network of radio observatories working together through a technique called Very Long Baseline Interferometry. By synchronizing observations from telescopes on different continents, the EHT creates a virtual telescope the size of the Earth, with a resolution sharp enough to see a black hole's shadow from millions of light years away. The observations were made in April 2017, but it took 2 years to process the data and produce the final image. The data volume was enormous, hundreds of petabytes, too much to transmit over the internet. Instead, hard drives containing the observations were physically flown to processing centers where supercomputers combined the data. Creating the image also required sophisticated algorithms to account for atmospheric distortion, instrumental effects, and the fact that the EHT did not observe the entire black hole simultaneously. The team developed multiple independent imaging methods to ensure that the result was not an artifact of any one algorithm. All methods produced similar images: a bright ring around a dark center, just as general relativity predicted. The size and shape of the shadow allowed the team to measure the mass of M87, about 6.5 billion solar masses. The asymmetry in the brightness of the ring, with one side brighter than the other, is caused by relativistic beaming. Material in the accretion disk is moving at high velocities, and the side moving toward us appears brighter because of Doppler shifting and relativistic effects. From this asymmetry, the team could infer that the black hole is spinning clockwise from our perspective. In May 2022, the EHT released a second image, this time of Sagittarius A star, the supermassive black hole at the center of the Milky Way. This observation was more challenging because ISCA A star is much smaller than M87 star, and the gas around it changes on timescales of minutes. Over the course of a night's observation, the accretion disk can look very different. The team had to develop new techniques to average many snapshots and produce a coherent image, but the result was worth it. Another bright ring around a dark shadow, confirming that our own galaxy harbors a supermassive black hole at its heart. The shadow's size matched predictions based on decades of tracking stellar orbits, providing independent confirmation of the black hole's mass, about 4 million suns. These images are profound. They show us what space-time looks like when it's curved so severely that light cannot escape. They confirm, in a direct visual way, that event horizons exist, and they demonstrate that general relativity holds true even in these extreme conditions, where gravity is strong enough to bend light into rings and cast shadows against glowing gas. The images also show the power of international collaboration. The EHT involves more than 300 scientists from dozens of institutions across many countries. It required coordination, trust, and the pooling of resources and expertise. And it worked. The images are a testament to human curiosity, ingenuity, and cooperation. Looking ahead, the EHT will continue to improve. More telescopes are being added to the network, increasing the resolution and allowing observations at different wavelengths. The team hopes to make movies showing how the gas around black holes changes over time, revealing the dynamics of accretion and the behavior of magnetic fields near the event horizon. These images are just the beginning. We've crossed a threshold, moving from inferring black holes from their effects to actually seeing them, or at least seeing their shadows. It's a new era in astronomy, one where the most extreme objects in the universe, once purely theoretical, have become visible, tangible, and real. The quantum edge, Hawking radiation, and the fate of black holes. In 1974, Stephen Hawking made a surprising discovery that changed how physicists think about black holes. He showed that black holes are not entirely black. Instead, they emit a faint radiation, now called Hawking radiation. And over immense timescales, they can evaporate completely. This discovery arose from applying quantum field theory to the curved space-time near a black hole's event horizon. Quantum mechanics tells us that empty space is not truly empty. Particle-antiparticle pairs constantly appear and disappear, emerging from quantum fluctuations of the vacuum. Normally, these pairs annihilate almost immediately, and their existence is fleeting and undetectable. But near a black hole's event horizon, something remarkable can happen. A particle-antiparticle pair can appear, and before they annihilate, the event horizon can separate them. One falls into the black hole, while the other escapes into space. To an outside observer, it appears that the black hole has emitted a particle. This is the simplified picture often presented, but it's worth noting that the actual mechanism is more subtle. Hawking's calculation doesn't rely on literal particles being split at the horizon. Instead, it's about how quantum fields behave in the curved space-time near the black hole. The field can be in what looks like a vacuum state to an observer far from the black hole, but near the horizon, the intense curvature causes this vacuum to appear as if it contains thermal radiation. The result is that black holes emit radiation with a thermal spectrum characterized by a temperature inversely proportional to their mass. This is called the Hawking temperature. For a stellar mass black hole, say 10 solar masses, the temperature is incredibly cold, about a billionth of a Kelvin, far colder than the cosmic microwave background. Such a black hole absorbs more radiation from the surrounding universe than it emits, so it grows rather than shrinks. But for a tiny black hole, the Hawking temperature is much higher. A black hole with the mass of an asteroid would have a temperature of several thousand Kelvin, hot enough to glow visibly. A black hole with the mass of a mountain would be even hotter, emitting high-energy gamma rays, and the smaller the black hole, the hotter it gets and the faster it evaporates. If a black hole does not gain mass by accreting matter, it will slowly lose mass through Hawking radiation. As it loses mass, it gets smaller and hotter, and the rate of evaporation increases. Eventually, in the final moments, the black hole evaporates explosively in a burst of high-energy particles. For a solar mass black hole, the evaporation time is unimaginably long, far exceeding the current age of the universe by a factor of 10 to the power of 57. Supermassive black holes will evaporate even more slowly. The universe itself, if current models are correct, will expand and cool for timescales that dwarf even these evaporation times. Black holes may be among the last objects to survive, cold and isolated in an ever-expanding cosmos before they too fade away. But very small black holes, if they exist, could evaporate much faster. Primordial black holes, hypothetical black holes that might have formed in the early universe, could have masses small enough to evaporate within the current age of the universe. Astronomers have searched for the gamma-ray bursts that would signal the final evaporation of a primordial black hole, but none have been detected so far. This absence places constraints on how many primordial black holes exist. Hawking radiation raises profound questions about the nature of information. In quantum mechanics, information about a system's state is never truly lost. It can be scrambled or hidden, but in principle, it can always be recovered. But if a black hole forms from matter and then evaporates into thermal radiation, where does the information about the original matter go? This is called the black hole information paradox. If the Hawking radiation is purely thermal, with no information about what fell into the black hole, then information is lost when the black hole evaporates. This would violate a fundamental principle of quantum mechanics. Various resolutions have been proposed. Perhaps the information is encoded in subtle correlations in the Hawking radiation, too delicate to detect, but present nonetheless. Perhaps it's stored on the event horizon itself, encoded in some way that we don't yet understand. Or perhaps the evaporation process is not quite as Hawking calculated, and there's a final burst at the end that carries away the remaining information. Recent developments in string theory and quantum gravity suggest that information is not lost, that it's encoded in the radiation in ways that are extremely difficult to extract, but technically possible. This resolution seems to preserve both general relativity and quantum mechanics, though the details are still being worked out. There's also the possibility that black holes don't evaporate completely. Some theories predict that evaporation slows or stops when the black hole reaches a certain tiny size, leaving behind a stable remnant called a Planck mass black hole. These remnants would be incredibly small and light, perhaps just a few micrograms, and stable against further evaporation. If they exist, they could be scattered throughout the universe, relics of ancient black holes, or even primordial black holes from the Big Bang. Hawking radiation has never been directly detected. The effect is far too weak for astrophysical black holes, but physicists have created analogues of black holes in the laboratory using sound waves in fluids or light in optical systems. In these analog systems, something like a horizon can form, and researchers have observed radiation analogous to Hawking radiation. While not definitive proof, these experiments provide strong support for Hawking's theoretical predictions. The existence of Hawking radiation implies that black holes have entropy, a measure of disorder or information content. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is surprising and deep. It suggests that all the information about a black hole is somehow encoded on its two-dimensional surface, a principle that has inspired the holographic principle, one of the leading ideas in quantum gravity. So black holes, once thought to be eternal, are not. They can evaporate, though the timescales are so long for astrophysical black holes that the effect is negligible. But the principle is profound. Black holes are not perfectly black. They emit radiation, they have temperature and entropy, and they connect general relativity with quantum mechanics in ways that still challenge our understanding. They are not just gravitational objects, but quantum objects as well, and their properties hint at a deeper theory that unifies gravity with the other forces of nature. Black holes, at the hearts of galaxies. At the center of nearly every large galaxy lies a supermassive black hole. This is not speculation or theory. It is supported by decades of observations. The Milky Way has one, with a mass of about 4 million suns. The nearby galaxy Andromeda has one, roughly 100 million solar masses. Messier 87 hosts a giant of 6.5 billion solar masses. These black holes are common, perhaps ubiquitous among galaxies. But why? Why do galaxies have supermassive black holes at their centers? How did these black holes form? And what role do they play in the life of a galaxy? The formation of supermassive black holes remains one of the great unsolved problems in astrophysics. There are several possibilities, but no consensus. One idea is that they grew from stellar mass black holes through accretion and mergers. A stellar mass black hole at the center of a forming galaxy could pull in gas and grow over billions of years. It could also merge with other black holes, increasing its mass with each merger. But there's a problem. Supermassive black holes existed surprisingly early. Quasars powered by billion solar mass black holes have been observed in galaxies less than 1 billion years after the Big Bang. That's not much time for a black hole to grow from a few solar masses to 1 billion, even with rapid accretion. The black hole would need to accrete matter at or near the Eddington limit, the maximum rate at which it can pull in material before the outward pressure from radiation balances the inward pull of gravity. Another possibility is that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar stage. If a large, pristine cloud of hydrogen gas collapsed without fragmenting into stars, it could form a black hole with thousands or even millions of solar masses right from the start. This would give the black hole a head start, making it easier to reach billions of solar masses by the time we observe distant quasars, or perhaps primordial black holes formed in the first fraction of a second after the Big Bang, served as seeds. If these primordial black holes had the right masses and abundances, they could have acted as gravitational anchors, drawing in gas and growing into supermassive black holes relatively quickly. Each of these scenarios has strengths and weaknesses, and the truth may involve a combination. But what is clear is that supermassive black holes were present early and have grown along with their host galaxies. There's a tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the mass of the galaxy's central bulge and the velocity dispersion of its stars. This correlation suggests that black holes and galaxies evolve together. They influence each other through a process called feedback. When a supermassive black hole accretes matter, it releases enormous amounts of energy in the form of radiation and jets. This energy heats the surrounding gas, preventing it from cooling and collapsing to form stars. Without this feedback, galaxies might form stars too rapidly, exhausting their gas in a cosmic blink. But the black hole's energy output regulates star formation, creating a self-balancing system. The black hole grows as it accretes, but its growth heats the gas, which reduces the supply of material falling into the black hole. This feedback keeps both the black hole and the galaxy in a kind of equilibrium. Observations support this picture. Galaxies with more massive black holes tend to have older stellar populations and less star formation. Galaxies with active, feeding black holes often show signs of outflows where gas is being pushed out by radiation pressure or jets, rather than falling inward to form stars. Black holes also play a role in galaxy mergers. When two galaxies collide and merge, their central black holes eventually sink toward the center of the merged galaxy. Over millions of years, they form a binary, orbiting each other while emitting gravitational waves. Eventually, they merge into a single, more massive black hole. This process has been observed indirectly through gravitational waves detected by LIGO and Virgo, and astronomers have identified galaxies with two active, supermassive black holes in their centers, systems that will merge in the distant future. The jets produced by supermassive black holes can extend far beyond the galaxy, injecting energy into the intergalactic medium. These jets can be millions of light years long, visible in radio observations as lobes of emission on either side of the galaxy. The energy carried by these jets affects not just the host galaxy, but also the surrounding environment, shaping the distribution of gas on the largest scales. So supermassive black holes are not just passive inhabitants of galactic centers. They are active players in cosmic evolution, regulating star formation, shaping galaxies through feedback, and influencing the intergalactic medium. Understanding black holes is essential to understanding how galaxies form and evolve. They are woven into the structure of the universe, from the smallest scales, where quantum mechanics and gravity collide, to the largest scales, where galaxies cluster and merge across billions of light years. Recent discoveries and the frontier of knowledge. Black hole research continues to accelerate. The year 2024 alone brought numerous discoveries that expanded our understanding and raised new questions. In February, astronomers announced the discovery of the fastest growing black hole known, consuming the equivalent of one sun's mass every single day. This supermassive black hole, observed as it was 12 billion years ago, powers the brightest quasar ever seen. Its voracious appetite and luminosity challenge our understanding of how black holes grow and how much matter they can consume. In the summer, observations confirmed an intermediate mass black hole in Omega Centauri, a globular cluster about 18,000 light-years from Earth. With a mass around 20,000 solar masses, this black hole fills a gap in the mass spectrum and provides clues about how supermassive black holes might have formed. The James Webb Space Telescope has been particularly fruitful, discovering supermassive black holes in galaxies from the universe's first billion years. Some of these black holes are more massive than expected for such early times, suggesting that they formed through unusual processes or grew extraordinarily quickly. One galaxy observed by JWST appears to contain a black hole so massive relative to the galaxy's stellar mass that it challenges standard models of black hole and galaxy coevolution. In another development, astronomers discovered a supermassive black hole consuming matter at 40 times the Eddington limit, a rate that theoretically should be unsustainable. The observation suggests that black holes can, at least temporarily, exceed these theoretical limits, perhaps through episodic bursts of rapid accretion. This finding may help explain how supermassive black holes grew so quickly in the early universe. The Event Horizon Telescope observed a powerful gamma-ray flare from M87 star, the first such observation from this supermassive black hole in over a decade. The flare provides insights into how jets are launched and how particles are accelerated near the event horizon, shedding light on the mechanisms that power some of the most energetic phenomena in the universe. Gravitational wave astronomy has also advanced. LIGO, Virgo, and CAGRA have detected dozens of additional black hole mergers, refining our understanding of the black hole mass distribution and merger rates. Some of these mergers involve black holes with unusual masses or spins, hinting at diverse formation channels. In a remarkable observation, astronomers using the Hubble Space Telescope and Chandra X-ray Observatory discovered a system with two supermassive black holes separated by just 300 light-years, both actively feeding. Such systems are rare and provide opportunities to study how black holes interact before they merge. Theorists have also made progress. New models of primordial black hole formation, incorporating corrections from quantum field theory, suggest that such black holes could exist without violating constraints from cosmic microwave background observations. This reopens the possibility that primordial black holes contribute to dark matter. Research into black hole evaporation has shown that Hawking radiation may not require an event horizon. Gravity and space-time curvature alone can produce similar effects, meaning that even objects without event horizons could eventually evaporate. This finding expands the implications of Hawking's work beyond black holes themselves. All of these discoveries illustrate that black hole research is vibrant and rapidly evolving. New instruments, both on the ground and in space, are revealing details that were unimaginable just a decade ago. The Event Horizon Telescope is expanding. Gravitational wave detectors are becoming more sensitive, and telescopes like JWST are peering deeper into the early universe. Each discovery raises new questions. How did supermassive black holes form so quickly? What is the nature of the connection between black holes and their host galaxies? Can we detect primordial black holes? And if so, do they constitute dark matter? What happens inside the event horizon? And what replaces the singularity in a complete theory of quantum gravity? These questions drive research forward. Black holes sit at the intersection of general relativity, quantum mechanics, thermodynamics, and cosmology. They are natural laboratories for testing our theories in extreme conditions. And they continue to surprise us, revealing new phenomena and challenging our assumptions. A gentle conclusion. So as your breathing slows and your mind drifts towards the edges of sleep, let's gently gather what we've explored tonight. Black holes are regions of space-time where gravity becomes so extreme that nothing, not even light, can escape once it crosses the event horizon. They form from the deaths of massive stars, from collisions in the early universe, and perhaps through mechanisms we have yet to discover. They come in various sizes, from stellar mass remnants to the supermassive giants at the hearts of galaxies. They are predicted by general relativity, the theory that describes gravity as the curvature of space-time. They have been confirmed through observations, through the motions of stars, through X-ray emission from accretion disks, through gravitational waves from merging black holes, and through direct imaging of their shadows. They exist, they are real, and they are scattered throughout the universe in vast numbers. Near a black hole, the laws of physics reveal themselves in their most extreme form. Time dilates, space warps, and tidal forces can stretch matter into impossibly thin strands. Yet crossing the event horizon of a supermassive black hole might be surprisingly gentle, at least initially. The extreme effects come later, deeper inside, hidden from view. Black holes feed on matter, and when they do, they shine. Accretion disks around them can outshine entire galaxies, and jets launched from near their poles can extend for millions of light years. They power quasars and active galactic nuclei, some of the brightest objects in the universe. They regulate star formation in galaxies through their energy output, shaping cosmic evolution on the largest scales. They merge, producing gravitational waves that ripple across space-time, carrying information about the merger to observatories on Earth. These waves have opened a new window on the universe, allowing us to observe events that produce no light, only the faint trembling of space and time itself, and they evaporate slowly through a quantum process discovered by Stephen Hawking. Over timescales that dwarf the age of the universe, black holes radiate away their mass and eventually disappear, though perhaps leaving behind tiny remnants or information encoded in subtle ways we are only beginning to understand. Black holes challenge us. They force us to confront the limits of our theories, the boundaries where general relativity and quantum mechanics collide. They raise profound questions about the nature of information, the structure of space-time, and the ultimate fate of matter and energy in the universe. But they also inspire us. They represent one of the great intellectual achievements of humanity, the ability to predict, through mathematics and logic, phenomena that were once unimaginable, and then to confirm those predictions through careful observation. They show us that the universe is stranger and more wondrous than we ever dreamed, and that we have the tools to explore its mysteries. So rest now. Let these ideas drift through your mind like stars moving across the night sky. You've journeyed through some of the most profound concepts in physics, through space-time curvature and event horizons, through accretion disks and gravitational waves, through singularities and quantum evaporation. You've touched the edge of the unknown, where our current understanding gives way to questions yet unanswered. And in doing so, you've participated in one of humanity's greatest adventures, the quest to understand the cosmos, to see clearly what lies hidden, and to grasp, even for a moment, the deep structure of reality. Thank you for joining me on this journey. If this exploration has brought you peace, if it's helped you set down the day's burdens and find a quiet place to rest, I'm glad. And if you'd like more of these gentle travels through science, more calm explorations into the mysteries of the universe, please consider liking this video and subscribing to the channel. Your support helps others find their way here, one curious mind at a time. Sleep well, dream deeply, And know that out there, in the vast darkness between the stars, black holes continue their silent vigil, bending light and time around themselves, holding secrets that we are only just beginning to uncover. The universe is patient. It waits for us to understand. And in time, step by gentle step, we will. Good night.